talk of the seminar series. Today we have Bethany Marsh, and she is going to talk about tau exceptional sequences. Thank you.
Thank you very much, Amina. So I'm going to try to write large, so please let me know if something goes wrong and it gets too small, and particularly on Zoom. So this is joint work with Aslak Bakke Buan. Okay, and the main idea is to introduce a generalization of exceptional sequences that behaves well in the non-hereditary case. And the work was motivated primarily by work of Igusa-Torodov. And they defined signed exceptional sequences in the hereditary case. So I'd like to start by saying a little about exceptional sequences. So standard setup, lambda will be a basic finite dimensional algebra over a field. Okay. So we know that lambda is isomorphic. Path algebra modulo admissible ideal I. And I is an admissible ideal. N will be the number of symbols isomorphism. Shall I call the rank? And our finite dimensional left lambda module. I would assume a module is basic. It's obviously not. Okay, so a lambda module U is said to be rigid if S1 vanishes. And then a sequence is exceptional if certain homomorphism groups and X groups vanish. And there can't be any homomorphisms back in the sequence and no extensions back in the sequence. So lambda exceptional. Sometimes called exceptional. So and no and if the length of the sequence is m, the sequence is said to be complete.
This is x1 again, is it?
Thank you. Yes, mistake. So here I mean xl. L greater than or equal to 1.
But above rigid is just x1.
It's rather
Rigid is just x1.
the rigid is just x1. Yeah. I think that's what I mean. Okay, so these were introduced in an algebraic geometry setting. On down. And then there was subsequent work of Crawley-Booby and Ringgold, who brought it into representation. Yeah, it could be that it's all the higher x vanished there. It could just be x1. Do you think it's all?
My memory is much larger.
But the point is, I'm focusing on, for these, I'm focusing on the hereditary case.
Right.
It
Didn't tell us that.
difference, so that's why I can't remember. Okay.
You had an idea of
Yes.
that. There was an I over there.
Sorry?
There's an I over on the left there.
There's an I.
Yeah. You haven't told us you're focusing on the hereditary case yet. You just did, but
The capital I, yes.
not hereditary yet.
Yes, exactly. So yes, let's go for that one. And in the hereditary case, that's equivalent to UI being rigid. Okay. Okay, so these behave very well in the hereditary case. In particular, the definition is easier. In particular, there are complete sequences, but not in general. There are algebras without complete sequences. You take this quiver here and factor out by the square of the radical, then the maximal length of a sequence is 1. You have to take the project. Okay, so how to get a good theory in a general case. So, how we did modules. Okay, so the hope is that we can use actually Igusa-Torodov's tau tilting theory to solve this problem. Here's how we do the right hand translation. Okay, and we have alternative notion of rigidity. What lambda? How rigid? On u tau u is 0. Okay, and this is related to classical rigidity. So u tau rigid module is always rigid. Okay, and if the projective dimension is at most 1, the converse holds. You can use the Aslak Bakke Buan formula to show that. Okay, so actually Igusa-Torodov consider tau rigid pairs. So we need to look at the support of a module in terms of which projectives map to it, or which don't. Of modules. Projective is a support tau rigid pair. So first of all, M is rigid. And secondly, HOM PM is 0.
You mean tau rigid then?
Okay, so by mod M, I'll mean the lambda are non-isomorphic. What PM? What P? What M? And if the total number of summands in P and M is the rank is equal to M, then we say that it's support tau tilting. And it might be that P is 0, and then N is a tau tilting. And we're going to want ordered versions of these. Okay, so it's convenient to just have one object rather than two. Okay, so we're going to represent them by the M will just be the degree 0 part in the derived category, and the projective will be a shift from logic. TB mod lambda, the bounded derived category. Identify M. And that's so we're working inside C of lambda, which is lambda plus shift of mod lambda in the derived category. And similarly, Y is a subcategory of mod lambda. C of Y was made Y plus the shift of Y. The ordered versions, so an ordered support tau rigid. Tilting object. Lambda. These curly letters for objects in C of lambda, so it's curly T1 up to TR. Okay, so these are indecomposable objects in C of lambda. And the direct sum is the corresponding set. So in particular, an indecomposable support tau rigid object is going to be either a tau rigid module or a shift of a projective. Slightly strange consequence of the definition. That's how it works. Because these are what these could be. These will be either tau rigid modules or shifts of projective. That's an indecomposable. Okay, and remember the tau tilting case, the support tau tilting case is the case when R is equal
So you're saying that you couldn't end up with something non-projective in mod lambda shifted by 1.
That's correct.
And why?
Because this direct sum here has to be support tau rigid. Okay, so it has to come, it comes from a support tau rigid pair PM. So by definition, a support tau rigid pair is a pair PM when we put a tau rigid module and shift of the projective. And they're the objects we're considering to be support tau rigid in C of lambda by convention, by definition.
If instead of mod lambda shifted by 1, you simply wrote add lambda shifted by 1, nothing would have changed.
Except later on, we will need the other shifts. So we need these categories here. So there'll be projectives in subcategories being considered later on. So we need the whole category C of lambda. But at the moment, we're only using the projectives. Okay, so now I'm to the signed tau section. So this is support tau rigid, support tau tilting in C of lambda. So in other words, it's of the form. Has to be of the form M plus P1, where P is projective. Okay, so in the hereditary case, a role is played by the orthogonal category. So with the 0, 1 pairs. These are the objects in mod lambda for which y is 0 and x, y is 0. Okay, and this is again a hereditary category, some smaller algebra. Okay, but if you're in a non-hereditary case, that's not true. You don't get a modular category for a smaller algebra. So this is the problem in generalizing. So let's write x per for on vanishing. And per x will be defined similarly. And we have what's I think now called the tau perpendicular. So we're going to take, we had a tau rigid module U. This was defined by Hassel, so we call it J of U. So this is U per intercept at tau U. So this is the natural thing to do if you're generalizing to the tau tilting theory situation. Instead of having the x vanishing, you have appropriate tau vanishing. Just be because we've got these shifts of projectives. it turns out that these categories do have good properties. They are wide subcategories of one lambda. So subcategory W mod lambda is wide. So it is closed. Kernels kernels and extensions. Okay, so this is going to be again an abelian category, and in a nice way that the kernels and co-kernels are the same as they are in the whole category. So you can have abelian subcategories that have a different abelian structure. They're not quite so nicely embedded. So this is a very strong notion of being an abelian subcategory. So theorem. Due to Hasso and then yeah, using if U is tau rigid, perpendicular is a wide subcategory. And if U is indecomposable, then U is actually equivalent to a module category, one less. So you have some way of going down. Just need some way of down. Okay, so now the definition of a tau exceptional sequence becomes a bit clearer. So, some natural number. Now I've got a sequence of indecomposable objects in C of lambda. So remember, these are tau rigid modules or shifts of projector. The shifts of projectors are the signed part of this. There are no shifts of projectives, it's not signed. So the one at the end has to be support charges. C of lambda. Okay, so that's a bona fide tau rigid module or shift of the projector. And could you look at the rest of the sequence? This is tau exceptional sequence for J of UR. in C of JUR. Okay, now the projectives in this orthogonal category will be distinct from the projectives in mod lambda in general.
It's not a signed tau exceptional sequence, it's a exceptional sequence usually.
Oh, is that a question?
The definition is not that this is a signed exceptional sequence. That's natural. To say that the last one is tau rigid and the next, the other ones would be a tau a signed exceptional sequence.
Thank you, yes. So you're saying I've missed out the word sign here. Yes, I think thank you, that's good. That's what I meant to say. Yeah. I put that in brackets. Let's not do that. Just stick to the side. If there are no shifts of projectives, it's that side. Okay, so an important point to note here is that tau in the algebra is not the same as tau in the subcategory. Tau rigid. Same. So if you had the algebra is go back to this two cycle, but now just factor out. By one composition of two paths. Okay, and if you take tau of 2, 1, it's 1, 2. Okay, tau, that's the injective 2, 1, is the projective 1, 2. Okay, so you can see there's a morphism from 1, 2 to its tau shift. So it's not tau rigid. But if you look at J of 2, that's just 2, 1. So that's equivalent to the A1 module category. So if you look at tau J2 of 2, 1, 0. So just working with tau in the subcategory. Like you need to use the equivalence between the subcategory and mod lambda prime, this other module category. And using tau in lambda prime. So this is equivalent to A1, but tau is 0.
You put the board down again so that the definition remains visible. Board in.
Oh, okay, thank you. So bijection ordered support tau counting. Under and complete sign. Right, sequence. So that's why we need the signed sequences, and Igusa-Torodov also need them in order to get this bijection. Where if you want to get all ordered support tilting objects, you need all of the signed sequences. And in fact, to get this bijection to work, we need to use two-term tilting objects. Derived category of projective lambda modulus. Tilting objects. We don't have a proof that sort of doesn't leave the module category, if you like. But of course, the statement itself involves shifts of projectives.
Just to clarify again, the ordered in the first definition is simply you take a support power rigid object and you order the summands.
That's right.
Nothing. If you change the ordering, you will different ordered object, and therefore it corresponds to a different one of these.
It might be helpful to look at an example. Let's look at so the AR quiver. Tilting module. Okay, so this means there are 12 ordered support type tilting modules. Each has two summands. So if you look at U, u is 1, j of u is 1, 2. Okay, so u is 1. You can't have a hom from 1, no homomorphism from 1, so 2, 1 is ruled out. You can't have a homomorphism 2, 2, which is tau of 1 is 2, so you can't have a homomorphism into 2. So these three modules are all ruled out. Let's just start with 1, 2. Is that a question? Okay, so j of 1. What, 1, 2. So you can see that's a nice wide subcategory equivalent to A1. So U is 2, J of U is 2, 1. One, 2, J of U is 2. J of 2, 1, 2 is 1. And remember, 2, 1 is not J, it's not tau rigid. In general, that's not a wide subcategory. If you take J of a non-tau rigid module. In fact, in this case, it is. It's 1. Yeah. So, okay, so they're the so tau perpendicular. How do these things look? So you have ordered for tau 13. On this side, we have signed tau exceptional sequences. So if we take take 2, 1, 2 as the second. J 2, 1, 2 is 1, so we have to put 1 here. It has to be a tau rigid. Okay, there's one other choice. So this has to be either a tau rigid module in J of 2, 1, 2, which is just 1. But that J of 2, 1, 2 is equivalent to A1, to the A1 subcategory, the representations of the point. So 1 is projective in the subcategory, so it can be shifted. Okay, so modules which are projective in the subcategory can appear as shifted versions. Okay, in fact, the way the bijection works, you will get the same object here, but then you have to put a different module. I can't explain how to do that. Sequences, right? So again, here. Exceptional sequence J of 1, 2 is 2. So we can either have 2 or the shift of 2. Ordered support tau tilting objects, so they can have shifts of projectives in them. That's the only thing that can be shifted on this site. These all really live in mod lambda. So you could put a shift of a projective in the ordering. That's all. And one shift of 1, 2, or one without the shift. Happen. The last object is actually projected in mod lambda, and then it can be shifted. The bijection is not too difficult to compute. You're applying the torsion-free part, torsion-free factor in a torsion pair. But in general, to actually compute the bijection, you need to pass to these tilting objects. Triangles there. So it can actually be quite difficult in practice to compute the bijection. Make a few remarks on the hereditary thing. So now there's no I. KQ. And rigid and coincide, and these two perpendicular categories coincide. And the sine tau exception sequence becomes sine exception sequence. Okay, and these were introduced by Igusa-Torodov. This was our starting point for the work. And they were here in picture groups, some topological consequences and motivation. Okay, so the sine exceptional sequence. So again, U1 up to UR. Decomposable in C lambda, and each UA is rigid or a shift of projective? Okay, but
Bethany, would you move the from Zoom? Would you move the board down, please, because it moves out of the picture frame when you move it up, and we only see sort of the last line of what you're reading.
I see this one. Is that what you?
Yeah, thank you. I mean, just as much as it's comfortable, but.
Okay. Yes. Yes. I think. Okay. Thank you. So E has to be projective in J ui plus 1 to UR. Okay, that's what was happening. This is a simpler version of the iterated wide subcategory we had in the tau exception. It has to be projective, but only in this orthogonal category here. So you end up signing non-projective modules. And then you have the vanishing. So UI, J. 0. I guess we need to. At least if that's a mod, if it's a module, that's right. Okay, so here you have to forget any shifts. Forget the shifts. Okay, so support tau tilting becomes support tilting. So we get the bijection. Well, we get a bijection, and it's probably the same as theirs. I think we don't know if that's true. We both get bijections in this context. Ordered support tilting modules. Complete same. Okay, and the ordered support key modules are in bijection with the cluster tilting objects in this context. In cluster category, okay, that's I think this is observed by Andrew Kubrick in 2011. Okay, and then these correspond to color. So, at least in the hereditary case, there is a relationship to clusters. In fact, these ordered clusters, yes, I should say, ordered. In fact, these ordered clusters are studied by King and Breslov. So they're studying mutations of ordered clusters, and there's a groupoid structure there. There's a relationship. What I talked about today. There's also some relationship to groupoid. I think that's in King and Breslov. So there's been a bit of subsequent work. There's work of Emre Sen, who looks at weak exceptional sequences, which exactly rules out these higher X vanishing that I missed out at the beginning. There's work of Mendoza and Treffinger, who look at stratifying systems, quasi-hereditary algebras, those kind of things. And my student Dixie Sapato has enumerated some of these sequences in Nakayama algebras. So the combinatorics that arises is quite interesting. And we wrote a sequel which is called a category of wide subcategories. So it's a category whose objects are the wide subcategories of the J of U's. And the morphisms come from the tau exceptional structure. And this has recently been extended by Buan and Hansen to the tau infinite, tau tilting infinite case. We look at the tau finite case. So I'll stop there. Thank you.
Thank you very much, Bethany. I will first get questions from the room, and then this will give time to the Zoom audience to either type their question. Yeah, please go ahead if you have questions or comments from the people in the room.
Only a typo. Is BMRT missing an R?
No.
There's different.
Marcus wasn't. It's a subsequent paper.
Okay, sorry. Okay.
So is there a version of mutation for assigned tau exceptional sequences?
That's a good question, yes. And
Can you repeat the question?
so let me repeat the question, yes, sorry, thank you. So, the question is there a version of mutation for assigned tau exceptional sequences? So for exceptional sequences, there's a notion of mutation. It's not cluster mutation, it's where you move one object to the left in a sequence, and then you need to see what's on the other side. We're working on that right now. That's what we're doing here with Aslak. We're trying to. In fact, that's what we've wanted all along. We've been trying to do that, and it seems quite hard. It's not entirely clear. It's only going to work a different way.
If you have this bijection, can you say that mutation is compatible with these objects in the side? Or you're looking on how do we formulate this mutation?
Yeah, exactly. I mean, you could mutate these. You could mutate these because they're talking. Mutate those. So that's not the classical rate mutation. Exceptional. So that gives you something different here. We could say some things. We could say things like if you mute, you could just commute two of these, as well as that you unmutate. So you've got things you can do on this side. Try to write down what happens on this side directly if you do that. So that's the approach we're taking. But there's still a bit of work to do on that. That's really what one wants. I think we could show in the Kronecker case this transitive rate mutation wasn't possible in certain sense. Yeah, it's a work in progress stuff.
Is there any other questions from the audience? Ralph?
Maybe just to clarify, in your rightmost column, there the signed exceptional sequence are those which have a shift in the first term, or which ones are the ones which are signed?
Okay, so the question is, in the second column here, which ones are the signed tau exceptional sequences? Are they the ones with the shift? So these are all signed. There are 12 signed tau exceptional sequences. So either they can be shifted or not. Okay, so that's the way we're using signed. So
If you delete the word signed, then you only have the other three. Or?
So if you delete the word signed, it's the ones without a shift.
Uh-huh.
Yes. So we have 1, 2, 3, 4. Yes, there are 4 tau exceptional sequences.
Here, maybe, yeah. Gordana has a question. Gordana, you can go ahead.
Yeah, well, thank you, Bethany, but I just think you put my name instead of Hugh Thomas' name at one point. So this seemed to be happening. You know, earlier the paper with Iyama, Demonet, and so on, it should be Hugh Thomas and it shouldn't be me.
Okay, right at the beginning. My apologies.
Yeah, that kind of happens often, that people mix this 2 T's, Thomas and Todorov.
Yes, so this is Demonet, Iyama.
Yeah, that should be Hugh Thomas. Okay.
Is there another?
Is it there? It's just above you.
Is it there? Oh, thank you. Yes. So it's here. This is what you're saying here.
Yeah, that's not me.
Many thanks.
Thank you.
Any other question from the Zoom participants or remarks? Don't see any. So let's thank Bethany again for this beautiful talk. And hope to see you next week. For the next seminar.
Thank you.